As you saw last Thursday, we started section 3, chapter 3, and the plan for today is to finish chapter 3. So let's recall what we were doing. So there was a topological part. So we talked about path homotopy. So this is about a situation where we have two paths, gamma 1 and gamma 2, which are maps from, say, unit interval to a domain G inside complex numbers. And they're homotopic. If, well, I'll write maybe shorter than the lecture and shorter than the notes I sent you as a scan. So if there exists a continuous map H from unit square to G with the property that H of anything 0 is gamma 1 of this thing, H of anything 1 is gamma 2 of this thing. Also, H should fix the end. H of 0 any lambda is gamma 1 of 0 is gamma 2 of 0, and H of 1 lambda is gamma 1 of 1 is gamma 2 of 1. So we talked about these. Then we talked about contractible loops. So this is maps gamma from 0, 1 to G. With gamma of 0 equal gamma of 1. Such equals, say, Z0. Such that gamma is homotopic to gamma 0, where gamma 0 is constant path with value as Z0. And using the notion of contractible loops, we talked about different kinds of these domains G. So we defined special G. So we talked about, let's say, 4 kinds of those, simply connected. This is the most important one, although the least easy to verify. So where every loop is contractible. Then there's another kind which I won't talk about in detail, contractible G. So another word for them, by the way, is null homotopic. Then star-shaped. G, and this is with respect to a given point Z node. And D convex. So, and we proved that the sequence of implications is down to the top. So D is the strongest, it implies C, which implies B, which implies A. So we are interested in these, but somehow we don't have tools to verify that some subspace is simply connected. But there are easy examples of those. For example, convex. So what I'll actually need today at the lecture is examples of convex ones, D. So a disk. So I'll draw it. Also half disk. I won't even name it, but half disk. Or actually any how it's called, sector of the disk, where this is less or equal than pi over than pi. So we'll use these. So examples of B, of C, apart from those in D, it's this one. So C without half line. So I'll write L greater or equal than 0. And another one is just the disk outside of the same. So star shaped is with respect to a given point. So the point I'm choosing is here. So this is at 0 on the same line. Now it's clear that it's star shaped. And here also I choose a point somewhere on the same line. It will be star shaped. Good. So also we started talking about Cauchy integrable theorem. Theorem. Cauchy integrable. Integral theorem. So we fix G simply connected open in C, and F is holomorphic in G. So holomorphic. Then, if gamma is a closed path, so a loop, in G, and then it follows that integral over gamma of F is 0. So we want to prove this, and we started the proof, and we actually did the most part of the technical work. So main statement. It's called Gursat lemma. So it doesn't really matter if we're in the simply connected situation. It's just f is holomorphic in some area, in some domain G, and nabla is a solid triangle so the inner part is also inside G. Then it follows that the integral along the boundary of this triangle, along the sides of this triangle, in some orientation is not important, you choose one, you enumerate the vertices and go from first to second, from second to third, and back. F is 0. And we proved this already, so this was our main achievement at the end of the previous lecture. So, to complete the corresponding section, we will prove the theorem in a rather special case, but it's the one we'll need. So G is star-shaped. And the path gamma is a staircase path. So star-shaped with respect to some point. So we don't do the general case. So general case, no please. However, as I mentioned, star-shaped is basically the only realistic example of contractible subsets we can handle, because of simply connected subsets we can handle. The more general ones we don't have tools to verify. So so here is the proof. So we have our star-shaped path, staircase path. Oh, I'm mixing two words. Staircase. So it's like this. Inside our G. So let's enumerate the points connecting the straight line intervals. Say starting from Z0, Z1, Z2, and so on. And Z0 will be also Zn. So our path gamma goes from 0, 1 to G, and gamma of Ti is Zi. And on the interval from Ti minus 1 to Ti, the point is going either along horizontal interval or along vertical interval. So the picture I drew at the previous lecture, at the end of the previous lecture, was slightly misleading. So here is the point with respect to which G is star-shaped. So maybe I should emphasize this remark. So G not the area inside gamma, is star shaped with respect to the z-naught. So to emphasize this, I even drew z-naught outside of gamma. And then I connect this point with vertices, and by definition of star-shaped, all these obtained triangles are completely inside inside G. So so each straight line triangle, solid triangle. Oh, no, that I don't like this. This will be yes. Sorry about this. This will be Z1, and this will be Z2, and this will be Z3. It's slightly different notation from the book, but it doesn't matter. So each solid triangle, and as I said, order of the vertices gives me orientation. So this triangle will be, I'll denote it by 3 letters, Z I minus 1, Z0, Zi. So from a point on the curve, we go to the center of this star-shaped area, and then we return to the next point of the curve, and then go back. Is inside G, because G is star-shaped. With respect to Z0. So call it just delta I, or maybe delta I minus 1. So we have delta 1, so on, and the last one will be delta n minus 1. What's important is that sides, again denoted by say Z I Z naught, belongs to the side to two neighboring triangles. But with opposite orientation. So it follows that sum of integrals over the size of these triangles I goes from 1 to n minus 1 of f. So of course it's the sum of integrals over the sides, and two of these will cancel out, and the third one will contribute to the total integral along the curve. So this is the integral over gamma of f. On the other hand, by the main lemma, the Goursat lemma, each integral is 0, because f is holomorphic inside this area. So then we obtain that the total integral is 0. So in a way, I won't write this down, but the total proof is a mixture of two types of considerations. There's analytic part, it's the lemma. If you remember, the proof of the lemma was completely analytic. We made these triangles subdivided to smaller, 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 and smaller ones, and then proved that the sum of integrals has to be 0. And the geometric one, which we consider this subdivision into triangles, for example, and so on. So it's clear that the general statement about just any path and any simply connected area is even more geometric. You need to approximate paths by star-shaped, by staircase ones, and so on. But I'll stay with this. So this is the precision of the proof I like, and I won't go deeper. So we proved the integral theorem, and let's write down the corollary from this. Mentioned before, and of corollary of analytic nature. So G inside C is simply connected, and F is holomorphic in G. Then, as we proved in section 2, and by Cauchy integral theorem, F has a primitive in G. So so in particular, now we have, so example, a y k0r without the point 0 is not simply connected. As I said, there are not so many tools for us at this point to see if something is not simply connected. Suppose it were, so proof. Suppose it were. Then f of z equal 1 over z, which is certainly holomorphic in this area. Would have had a primitive. But then if we take 2 points, for example, let's say there's a point 1 here, and let's consider path starting at 1 and ending at 1, like this. So it's a unit circle. And let's say gamma 0 is just the constant path. so integral over gamma of 1 over z dz would be equal to integral over constant part, which is certainly 0, and this would be 0. Sorry, gamma 0. But this is simply wrong. So by now it's Tuesday, so many of you have seen this at TA session, and those of you who have not, well, tomorrow. So this is wrong. So this integral is not 0. And actually, you can distinguish how many times the path goes around 0. And the integral depends not only on the image of the path, but on the number of times you go around. So, yeah, this is a contradiction, which means that throwing away the point from the disk makes it non-simply connected. Good. So, another application is like this. So it's actually the beginning of next topic towards Cauchy integral formula. So suppose we have the same situation more or less as here. So we have G, which is a domain in C, and Z0 is a point in G, just like we had the point 0 inside the disk. And suppose that we have a function f, which is holomorphic in G outside of this point. And now, suppose that we have, so we have this C, and we have Z0, and we have two paths, two closed paths, so two loops, I would say, around this point. Call them K and C. So K and C closed paths. Closed curve. Closed simple curves. I don't want them to self-intersect. In G without the 0. Which are close, and I'll explain what it means for them to be close. So I'll first write the statement, and then we'll understand what the word close means. So then the integral of f along C equals the integral of f along K. So now I'll try to explain what the word close means. Here it's not a mathematical word, it's a meta-mathematical word, but it will be a technical condition. Remark, being close means. So first of all, let's say that they are oriented in the same way. Oriented So let's say clockwise, counterclockwise. But second, this will be technical, but this will be exactly what we will be checking. So imagine two closed curves, and the condition is that inside G without Z0, you can make cuts like this. A few, I don't know how many. Let's say 4 on this picture, but in general it can be any fine to many cuts. In such a way that each piece totally lies inside some subset Gi inside G, which is star shape. Okay, so doesn't matter how G itself looks like. We also threw away, inside G without the 0. It's important that we stay outside of this point. So, so this is my Gi. So the condition is technical in the sense that I chose it exactly in such a way that the integral of, so that f would be holomorphic inside. The area Gi, the domain Gi would be star shaped, and the closed curve obtained like this would be a closed curve inside a star shaped domain. So it's a technical condition. It's more obvious when you draw it than when you explain it in words. But the outcome call this piece Ci, this piece Ki, this piece Li for left, and this piece for Ri for right. And of course, Ri equals Li plus 1, because they go one after the other. So the outcome is that this curve, which is you start by Li, then you compose it with Ki, then you compose it with Ri, and then you compose it with Ci, in the sense of composition of paths, which is actually in the handwritten notes I sent you. So it's a closed curve in a star-shaped domain. Gi. And of course, my function f is holomorphic in Gi, because Gi is in the part where f is holomorphic. Okay, so now it's clear how to prove what I wrote here. So we want to say that the integral here equals the integral here. And then we use the same idea as in the proof of Cauchy integral theorem, sorry. So prove that the integral over C of f equals the integral over k of f. So first of all, as we noticed, f is holomorphic in ci. These are this ci ri ki li is closed curve in GI. Then it follows that the integral over E, so call this gamma I over gamma I of f is 0. Now let's see what we get. So let's take the sum of integrals of f along this gamma I. So on one hand it's 0, on the other hand it's sum of integrals over Li f plus sum of integrals over Ri f, and these cancel out. Together give 0 because I is the next Ri plus 1. They are oriented in the other direction. And then plus sum of integrals over ki f and plus sum of integrals over ci f. So 0 is so we get that. The sum of integrals over ki's of f plus sum of integrals over ci's of f is 0. But so let's look again at the picture. So there's inner and outer closed curve, and both of them are divided. So when we decided in which order we go around, we oriented them in opposite directions, so that the total orientation would agree. So notice that K is composition of all ki's, but C with opposite orientation, so going around C clockwise, is composition, well, actually I put the sign here, minus C, so the C with opposite orientation is composition of all Ci. So then so this formula reads as integral of k of f plus integral of over minus c of f is 0. But this one is minus integral over c of f. So we know that changing orientation changes the sign. So this is exactly what we wanted to get. So let's return to this picture. As you see, this condition of two closed paths, two closed curves, two loops being close to each other is something you need to verify. But in the proof of of Cauchy theorem, Cauchy integral formula, we will have very explicit and very concrete small c and big K, for which this condition will be clear. Okay. So, now let me probably finish the hour with formulation, with formulation of Cauchy integral formula. So we have a holomorphic function f in some domain G. So then it turns out that the value of this function at each point in G is completely defined by a certain integral, which is called Cauchy integral. So let's say that we have a disk K, K, R. This is the disk inside G. Actually, in such a way that even its closure is inside G. Then, for every point inside, we have that the value at this point is expressed as an integral over the circle, which is the boundary of the disk. Of the function f of z divided by z minus 0. So this is the formula itself. Just notice that since f is holomorphic in G, and 1 over z minus z0 has the only point where it's not defined when z equals z0, g of z, which is f of z divided by z minus z0, is holomorphic in G minus the point z0. So that's where we'll start applying considerations of this kind. So another remark is more philosophical. So if you look at this formula, it should be completely mysterious for you, because left-hand side of the formula is local. So it's value at z0, right? So it's something which is defined at that point. But right-hand side of this formula is global in the sense it depends on the value of f of z, well, where restricted to this probably absolutely huge circle like this. So let's think again, and then there'll be a break. So we have this, everything is inside G. So we have this circle, which is far, far away from this point. So it's there's a center somewhere at some A, and then there's some point Z naught somewhere here. So we can evaluate, so we know the function a priori. F only, so we know that it's holomorphic, but we know its value is only restricted to this boundary. And knowing that, we recover the value everywhere inside this disk. See, so it's something strange, because so counting on our real analysis intuition, knowing the function at some small neighborhood doesn't allow you to know it very far. You can modify the function so that it will stay the same around a given point, but will completely change something very far. And you can do it in any realm. You cannot do it in polynomials, but in any other class of functions you can imagine on real line, you can do it easily. So modify the function far away from the given point. In complex analysis, this is impossible. If you have the value of the function in here, you will completely know it everywhere inside. Although this inside is very far from every point on the boundary. Good. So let's stop here. In the remaining hour.